Well, hello there. Here is another example for computing a confidence interval. The setting here, though, is a little bit different than the previous one. Here we're estimating a mean, but sigma is unknown. Sigma, again, is the population standard deviation, and here we're assuming that it's unknown. And this is actually a more realistic setting for sigma to be unknown and trying to estimate the mean in this problem. But in this example here, we've got a machine that produces ball bearings, and it's set so that the average diameter is supposed to be ½ inch. Well, is this the case? Well, in an attempt to answer this question, let's estimate the average diameter with a 95% confidence interval. Okay, so to generate a confidence interval, we need data. We need sample information to make inferences upon this average diameter. Okay, the data here is a random sample of 10 ball bearings, and we get the following diameters. So the first ball bearing had a diameter of 0.48 inches, the second had a diameter of 0.5, the third had a diameter of 0.49, and so forth. And so this machine that's making these ball bearings, these are 10 ball bearings, or the diameters of 10 ball bearings that have come off the machine. And we want to say something about the average diameter of all the ball bearings that come off the machine. Okay, let's assume that the diameters are approximately normal. This may be a realistic assumption. We could, if we know something about this machine and how it produces ball bearings, this actually may not be too far-fetched. We could also check this assumption by looking at the histogram of the data. That's one way to look at it, or we could look at the box plot of the data to see if those are symmetric, and then that might lend to the assumption of a normal population. Okay, well, first thing, what I want to do is specify the parameter of interest. So I'm going to let this be the first thing here, specify the parameter of interest. Well, we're looking at mu, that's our parameter of interest. We want to say something about mu, and it's the average diameter of all ball bearings produced by this machine. Okay, well, we want to say something about this average quantity here, and the reason is, if this average diameter is, say, pretty far away from 0.5, then maybe our machine is out of whack, and we need to go back and calibrate it or fix it up, stop production, and kind of rethink how these ball bearings are coming out of the machine. So we want to say something about mu. That's our parameter of interest. Secondly, we need to justify the interval formula that we use. All right, now I'm going to turn over on the back of this page here and just write out the 3 interval formulas that we have for estimating a population mean. We have this one, x bar plus or minus z times z sub alpha over 2 times sigma over the square root of n. We have x bar plus or minus z sub alpha over 2 times s over root n. And then lastly, we have x bar plus or minus t sub alpha over 2 times s over root n. So we got to ask ourselves, which one of these 3 do we use, or can we use any of them? Well, the first formula requires that sigma is known, the population standard deviation. Well, nowhere in the problem setup did we say anything about knowing sigma. And you don't get sigma from a sample data set, so we can't use this one. Okay. Well, what about this formula here? Basically, going from here to here, all we've done is replace sigma with s. And this is a valid formula if n is greater than 30. our sample size is large, we can use that formula. Well, that's not the case here. N in this problem is 10. We only have 10 ball bearings that we've sampled from this machine here. So we can't use this formula. What about this last one? This one works in the small sample case, but we have to have the condition that the data is normal. And well, we assume that the diameters are normal, so this one actually will work for us. We have a random sample. Sigma is unknown, and we have normal data, so we can use this interval here. So what I'm going to say here is we will use x bar plus or minus t sub alpha over 2 times s over the square root of n. Sometimes this is called the t interval, but we'll use this formula because one, we have a random sample, which is a requirement to use this formula. 2, sigma is unknown. And lastly, 3, move up here a little bit. Our population is approximately normal. Okay. I hope I didn't confuse you. This 1, 2, and 3 are different than these, but these are the 3 reasons that allow us to use this formula here. Thirdly, so what I've done here is this is actually 1 is I specify the parameter of interest. 2, this is an interval formula that we're using, and now we've just justified it because of these 3 statements here. Lastly, what I want to do is actually now compute the confidence interval. What is that? Well, so I'm going to use this formula. I need x bar, I need a t percentile, I need s, the sample standard deviation, and n is my sample size. Well, so let's see here. We know from the data n is 10. Okay, that's pretty straightforward. Now, we also need x bar and s. And x bar is simply, if you recall, the sum of the observations over n. And if you were to sum up these 10 observations and divide by 10, you would get 0.493. So this is a previous idea that I'm not going to spend the time to flesh out the details of computing x bar, but you can verify that it's 0.93. Also, s here, if you recall, s, the sample standard deviation, is the square root of the sum of the square deviations divided by n minus 1. Well, again, I'm not going to go through that long computation for these data points, for these 10 data points here. This is something that you've done in the past and hopefully have a good handle on. But if you work through this, you'll see that s is 0.022. This is a reflection of the variability in the diameters of those 10 ball bearings. Okay, now what else do we need? So this is from the data, but to use this formula we need t. Alright, well with the t, that depends on the degrees of freedom, right? So if you recall, the degrees of freedom is n minus 1. So here we got the degrees of freedom is 9. Okay, so let me make a statement here. Also, the degrees of freedom is 9. And what about t sub alpha over 2 then? So I'm looking at t sub alpha in this case is 0.05 because I've got a 95% confidence interval. So I've got t sub 0.025 that I'm looking for, and that's with 9 degrees of freedom. Well, I'm going to have to use my t-table for that, and from the text here, the t-table, trying to get it on the camera. Hopefully it's coming up okay on your screen, but here's t sub 0.25, and degrees of freedom with 9, the t critical value is 2.262. Okay, so 2.262 is my t value. Now the rest of the problem is really pretty straightforward. So we just plug in here. So we have x bar plus or minus t sub alpha over 2 times s over root n. So just plug it in here. We got 0.493 plus or minus 2.262 times 0.022 divided by the square root of 10. Okay, so just plug it in there. Now let's simplify, or let's begin to simplify. Here we go. So 0.493, this is my sample mean. Based on it, I'm going to add and subtract a little bit to try to infer something about the population mean. Okay. So what do I have here? It turns out if you do this computation in here, you get 0.0157. And again, this number is called the margin of error. We talked about that before. And if you add and subtract the margin of error to this value here, the lower bound of the confidence interval becomes 0.477, and the upper bound becomes 0.509. Okay, so this, we are 95% confident that the average diameter of all ball bearings that come off this machine is between these two values here. It's somewhere in here. And so maybe if you're not just super conservative with your machine, you could say, well, I don't have evidence to say that 0.5 is outside of this interval, so maybe it's okay to continue with the machine that's producing these ball bearings at this point. This is an example for computing a confidence interval on a mean when sigma is unknown.